Hi everyone. So I wanted to make this video just solving the quiz from last week. And so you can use this as a reference if there were problems that you found tricky. So this first problem, there's this table of positions as a function of time, and you're asked to find displacements, average velocities, and initial and final velocities for each time interval. So let's work through that. So the idea is to work through it, first finding the displacements, then using the displacements to calculate the average velocities, and then using initial and average velocity to get final velocity for each time interval. That's the basic idea. So let's walk through how that works. So the first one, the displacement during the first interval would just be the position at time equals 2 minus the position at time equals 1. So that one's just 3.2 meters. The displacement for the second time interval is the position, so that's from 2 to 6 seconds. The position at 6 seconds is 28.8. The position at 2 seconds is 3.2. So the displacement during that interval should be 25.6, which is just the difference. And then similarly, the position at 9 is 64.8. The position at 6 is 28.8. So 36.0 is the displacement there. Okay, the next step is to calculate the average velocity. So I'll write some work in the below here. So average velocity is always defined as the displacement over the time. So this is for some particular time interval. So for each time interval, we can look at displacement over time of that interval. So for the first one, the average velocity from 0 to 2 would be the displacement over the time interval, which is 2 seconds. So that's going to be 1.6. For the next one, the displacement from 2 to 6 is 25.6. And the time, the length of that time interval is 4 seconds, because 2 to 6 seconds is 4 seconds long. So if we do 25.6 over 4, we get 6.4. And then for the last one, 36 over 3 gets 12 meters per second. Okay, so then now we've got our average velocities for each time interval. To get the final velocities for the interval, then now we're going to work across like this. So because we're going to use the initial velocity plus and also knowledge of the average velocity to get the final velocity. And what we're using there is that this other way of calculating the average velocity, which is the initial velocity plus the final velocity of an interval divided by 2 is equal to the average if the acceleration is constant, which it is here, as stated in the problem. So in the first case, and we could go through and calculate all of this out, and maybe we should. So in the first case, the average velocity is 1.6. So for the first case, we have 1.6 is the average. So 2 times V average equals VI plus VF. So for us, V average is 1.6. So 2 times V average is equal to VI plus VF. VI is 0 though. So 2 times V average is 3.2. This is 0, therefore VF is 3.2. I'll write that in. The way to think about that too is that the average velocity always falls at the midpoint of the initial and final velocities if acceleration is constant. So initial 0, velocity increases to 1.6 at the average, so it's got to increase 1.6 again to get to the final velocity. That's what happened there. The initial velocity of the next time interval is 3.2 because the initial time for the next interval is 2 seconds and the final time for the first interval was 2 seconds. So now it's the same kind of thing where we've got 3.2 is the initial, 6.4 is the final. We could calculate it out using this equation, which you're certainly welcome to do. What I'm going to do is I'm just going to say 3.2 to 6.4 gets an increase of 3.2 meters per second. So the final will be an increase of 3.2 over 6.4. So that means the final's got to be 9.6. And so the initial of the next one is 9.6. So now 9.6 to 12.0, the increase there is 2.4. So I know I have to have 12 plus 2.4 to get the final. So that's 14.4. And that's how I worked out the table there. There are a lot of ways to calculate the acceleration, which is asked for in part B. The acceleration is constant though. So we can, if we know that the acceleration is the change in velocity over change in time, we can take any time period to calculate the acceleration here, because no matter what time period we take, the acceleration will be constant. So I'll do that just for the first time period. So I can take the change in velocity from 0 to 2 seconds was 3.2 minus 0. That's the change in velocity. So the change in velocity was 3.2, and the time period was 2 seconds. So that's 1.6 meters per second I can do that for any time interval. So if I did that for like the whole 9 seconds, my final velocity would be 14.4. My initial velocity would be 0. Take that difference, divide by 9, and I get 1.6 again. You can do this for any time interval, and it should work out. So that's number 1. All right, number 2. So we got the flabbergasted flamingo here. Calculate the flamingo's average velocity over all 3 seconds. So we know that the flamingo runs 6 meters in the first second, 10 meters in the second second, and 14 meters in the third second. So the total displacement for the flamingo over all 3 seconds is 6 plus 10 plus 14. That's 30 meters. So the average velocity is the displacement over the time. So that's 30 over 3 is 10 meters per second. There's other ways to get this. I think this is the most straightforward way. You just add up the displacements, divide by the time. That's the average velocity. How do you get acceleration here? There were a lot of solutions that looked something like, oh, the average velocity goes from 6 meters per second to 10 meters per second to 14 meters per second. So there's a difference of 4 meters per second each time. Therefore, the acceleration's 4 meters per second per second. And 4 meters per second is the right answer, but that reasoning isn't totally complete. So let me explain the way I'm thinking about this to kind of tighten up that reasoning a little bit. So if you look at 6 meters per second, 10 meters per second, and 14 meters per second, those things represent the average velocity from 0 to 1 second. This is the average velocity from 1 to 2 seconds. And this is the average velocity from 2 to 3 seconds. So these velocities happen, or they're the same as the instantaneous velocity halfway through the time interval. So if the acceleration is constant, I started at some initial velocity for each time interval, some final velocity for some time interval. The average velocity will be the same as the instantaneous velocity at the midpoint of the time interval. That means that this is the same thing as the velocity, and I'll write it instantaneous here, at t equals 0.5 seconds. And this one is the same for t equals 1.5 seconds. And this is the same thing as the instantaneous velocity at 2.5 seconds. So now we have velocities at particular times, and I can apply acceleration is a change in velocity over a change in time. So I could take, say, the change in velocity between 6 and 10. That would be 10 minus 6 is 4. That's over a delta t of 1.5 minus 0.5, because this velocity happens at 1.5 seconds. This velocity happens at 0.5 seconds. And so this ends up being 4 over 1 is 4 meters per second. And that's the acceleration. Lots of people got this result, but without working through the nuance there of what the delta t would actually be if you're using these average velocities to calculate acceleration. So that's my work through the solution here. Let me know if you have questions, and I'll talk to you soon. Bye.